Okay, I want to reuse an old video for this new class. It's supposed to be Algebra 2 and linear programming, so you can skip this very first page that I've got marked. The next page is going to be talking about finding the vertices when you have that system of inequalities. So you have two or more inequalities, how do you find vertices? So if we covered that in class and you're comfortable with it, you can even skip that page as well. But definitely skip this one. And you want to go on to the page that starts with optimization, because that's just another word for linear programming. So it'll be short from there, and we'll make sure we cover it and practice it in class. Okay, so we could actually have more than two separate inequalities. We can have three, okay? So let's graph this system of inequalities on the same coordinate axis. So there's my x, and there's my y. Let me do the first one in red. X has to be greater than 0. Now, of course, x equals 0 is this horizontal line, right? So if I want to be greater than that, I'm this direction. That's the first one. Then the second one, let me see if I can graph this one in blue. Y is greater than 0. Well, here's y is equal to 0, okay? If I want to be greater than that, I'm shading above like this. So far I have the double shaded is the first quadrant, if you would. Okay? So that's my double shaded, so far that's where I'm at. And then I have to do this last one. So let me try maybe green. So I want to graph that line. I'm going to have to switch it, of course. Less than negative x plus 4, or y is less than negative 1/2 x plus 2. Let me go ahead and put that as an equal sign as the boundary line, starting at 2, and then go down 1 over 2, down 1 over 2. Oops, doesn't have to go any further than that. So that's the boundary line, and I'm not even going to bother really going past the first quadrant. I know I want to be less than, so that's going to be this way. So what's interesting is now I've got this little triangle shape. It's now become a bounded region. Okay, there's no, if you put somebody inside your region, there's no getting out of it. Okay. And I can describe this, it certainly looks like a triangle, by the vertices. Okay, so what we're going to talk about is this point here, this point here, and this point here are vertices. Okay, so the corners of your triangle. So how do you calculate those? Well, the one is easy. 0, 0. Got that one. We also can do this one fairly easily because that was from this y-intercept right here. So 0, 2. How am I going to find that vertex? That one's going to be a little trickier because if you remember, I didn't quite hit that spot when I was doing my slope on that last line. But I do know this about that point. I know this is y is equal to 0, and what else do I know about that point? I know it's on the green line, the green boundary line, so y is equal to minus 1/2 x plus 2. I know those two things are both equal, are both true for this point. So what do I have? I have a system. I can solve this system for the xy point right there. So let me make a substitution that y is equal to 0 in this. Okay, so 0 is equal to minus 1/2 x plus 2. So let's see, I got 1/2 x is equal to 2, or x is equal to 4. So I get x is equal to 4, and of course I know that y is equal to 0. So let me go down here. My last vertex then is 4, 0 is my last vertex. Okay? So let me give you another one of these kind of things to try. Okay, so here's your new problem. That is a negative 2/3 x plus 5. Graph it, do your shading, find the vertices for this system. Okay, my answer is 0, 0, 0, 5. And my last point, 15/2, 0, I was kind of tempted, I'm not quite sure what I did wrong with my graph. I was kind of tempted to say, ooh, there's the answer right there, but I thought I would double check, just in case it's not an accurate graph, which it wasn't, to find out where exactly the lines meet. So obviously this line right here is meeting with this diagonal line. This is the line y equals 0, and this is the line y is equal to minus 2/3 x plus 5. So those two lines intersect at that last vertex, so I solve the system and find x equals 15/2, which is, you know, the correct answer. Alright, let's try something new with this then. Okay, we're going to start talking about optimization. Optimization can be either minimize or maximize, okay? We tend to want to minimize cost and maximize profits, okay? So optimization is kind of a general term for either one of those. There's usually some sort of equation that you're trying to optimize. Maybe that equation is describing your profit, and you want to maximize it. So let's say I have something like f of xy is equal to some function 4x minus 2y. Now, the problem is, you know, x can't just be anything and y can't just be anything. You have what's called constraints. And these constraints limit what x and y can be. And they tend to take the form of a system of inequalities. So you might have some constraints that look like this. Okay, so those are my constraints. They should look familiar. I should be able to go over here, draw the solution for this system of inequalities. So I'm in the first quadrant, x is greater than 0, y is greater than 0, and then I have my last graph, 1, 2, 3, 4, 5, 6, 7. I'm going to go down 2 over 1, down 2 over 1, down 2 over 1. Oh yeah, I did that again. Down 2 over 1. So I have this, I fill in the less than, and I have this. And what I've drawn, the shaded area, is the solution to those three inequalities, is what I call a feasible region. Okay, so x and y can be anything as long as that point lies within the feasible region. So those are the only things I can consider as for my x and y values when I'm trying to maximize this function. Okay, so we have to make sure x and y lies in there. Now here's the interesting part about all this. So you got to get really kind of pumped up about this. The min or the max occurs at the vertices. That is huge. Okay, whoever came up with this was a genius, okay? Because I don't have to test all these infinite number of points inside this feasible region to see which one gives me the maximum value of the function. I just have to test these 3 points that are the vertices. So remember how we found vertices before. My vertices were, in this case, 0, 0. Then I've got the what, 7, 0. And I've got to find this one. So let me work on that one. Okay, so that last vertex is 7/2, 0. Alright, so there are my 3 vertices, and let me show you what I'm going to do with those on the next slide. Oops, I meant to say the vertex here was 0, 7. So that fixes that. Sorry about that. I owe somebody a Jolly Rancher. Okay, so I'm trying to recap what we had, and we had, of course, the vertex was 0, 7. Okay, x was 0, y was 7. So now, what are we going to do? I'm trying to maximize this function. Find the value of f. That's the biggest number. And what are the x's and y's? So, I'm going to make a table of values, make a chart, where I put one vertex over here, and I evaluate the function at that vertex. So, the first vertex was 0, 0. So I'm going to figure out what is the function when x is 0 and y is 0. So when that's true, I have 4 times 0 minus 2 times 0 And of course the answer then is just 0. Okay? Then I'll try my second vertex, which is 0, 7. Figuring out what the function is, at that point I have 4 times 0 minus 2 times 7. That gives me a minus 14. Ooh. Then I have the last one. I have 7 halves, comma 0 as the last vertex. I'll figure out the function when x is 7 halves and y is 0 and get 4 times 7 halves minus 2 times 0. So that becomes, look at that, plus 14. So now you have to ask yourself, which one of these numbers is the largest number? Oh, this one is the maximum value. Okay, so that's the maximum value of the function 14, and it occurs, because you got to know where to set, your production at, where to put that sort of thing at. That occurs when x equals, right here, 7 halves, and y is equal to 0. So that sort of tells you how to operate your business. Okay? So that's linear. That's called linear programming. Sometimes we're calling it optimization in this book, but either one's a good way to talk about it. So I'll give you a problem. Okay, let's just say we've already done the hard part, finding the vertices, okay? And it came out to be this sort of a quadrilateral shape instead of a triangle. So I have these 4 vertices that I've labeled 0, 0, 0, 7, 4, 3, 5, 0, okay? And I want you to, this time we'll try and minimize, so maybe we're talking about costs, the function when it's 3x minus 2y. Which one of those vertices is the correct answer for minimizing the function? I'm going to pause it and we can check our answers. Okay, and in this case I have to test all 4 vertices. I come up with the function values. The smallest one, negative 14, is your minimum, and just tell me where that occurred and you got the right answer. Okay, so we're going to do a lot more practice because things, how do you find this vertex? We'll do that in class, but basically, you know the equation of this line. You know the equation of that line. So where's the inner point of intersection? You'll find it through elimination or substitution, just a system of those 2 lines. All right, then we'll practice in class. See you then.